What's going on, guys? Justin here, and welcome to our first example video following our course on abstract algebra. Now, today's video is going to be reviewing some basics of sets and functions, as well as relations and equivalence relations. So let's go ahead and get into this first example. So this first example says, suppose R is an equivalence relation on a set A with 4 equivalence classes. How many different equivalence relations S on A are there for which R is a subset of S? So right away, I want to note that we can create a new equivalence class from R by combining existing equivalence classes. Since we know R has 4 equivalence classes, we can let A be represented in the following way, where it is the disjoint union of those 4 equivalence classes. So we'll have, let's call them A through D. So we'll have A disjoint union B, disjoint union C, and lastly, disjoint union D. Great. So from here, I want to note that S can have 1, 2, 3, or 4 equivalence classes, where 1 and 4 are sort of trivial. So we're going to go ahead and list all of those equivalence classes, which is sufficient to show how many equivalence relations there are, as the equivalence classes define the equivalence relation. So let's go ahead and get started with the case where S has 1 equivalence class. And like I said, this is going to be pretty trivial, as this will just be A union B, union C, union D. And I'm not going to explicitly note that these are disjoint unions, but by definition, equivalence classes are disjoint. Great. So next, let's get into the cases where S has 2 equivalence classes. And so we can represent the cases where S has 2 equivalence classes in the following way, where we have 2 sets of 2 equivalence classes merged together. Then we'll also have sets of 3 equivalence classes merged together and the remaining equivalence class. So let's go ahead and start with the groups of 2 and 2. So for the first one, we'll have A union B and C union D. And then for the next one, let's do A union C. And then we'll have B union D. Then for the next one, let's have A union D and B union C. And that will be all the possible cases where we have 2 sets of merged equivalence classes. So next, let's do the ones where we have 3 merged classes and then 1 remaining class. So let's start with A, B, and C. So we'll have A union B, union C, and D. Then we can go ahead and do the next one. Let's just do A union C, union D, and just B. And then we can do the next one. Let's ignore C this time. So we'll have A union B, union D, and just C. And then lastly, we'll ignore A. Let's do B union C, union D, and then just A. Great. So far we have this one case where S has 1 equivalence class and these 7 cases where S has 2 equivalence classes. So next, let's do the ones where S has 3 equivalence classes. And that will just be the pairs of, we'll merge 2 of these equivalence classes together and then 2 remaining by themselves. So let me go ahead and write that out. We'll have case 3, which is when S has 3 equivalence classes. All right, so starting off, let's go ahead and merge together A and B. So we'll have A union B, and then we'll also have just C and just D. Next, let's union A and C. So we'll have A union C, and then we'll have B and D by themselves. And then we can union A and D. So we'll have A union D, and then B and C will be by themselves, so we'll have B and C. And now we can't union A with anything else, so let's go ahead and union B with something. So let's union B and C first. So we'll have B union C, and then we'll have A and D by themselves. And then let's go ahead and union B and D. So we'll have B union D, and then that will leave A and C by themselves. And then lastly, we can union C and D, and then that will leave B and A by themselves. So we'll have C union D, And then, like I said, we will have A and B by themselves. Great. So that is 6 more equivalence classes there. So we have 6 here, 7 here, and then the one up top. So that's going to give us a total of 14. But we haven't done the case where S has 4 equivalence classes, which is just going to be when S is equal to R. So case 4, S has 4 equivalence classes. And like I said, that's just the case when S is equal to R, so there's only one case. So if we add all those up, we get 1 plus 6, which is 7, plus 7 is 14, plus 1 is we have 15 total possibilities. Great, so let's go ahead and get into the next one. So for this one, we are going to define a relation R on the integers as x is related to y if and only if 5 divides 2x plus 3y. And we want to show that R is an equivalence relation and describe its equivalence classes. So in order to show that a relation is an equivalence relation, we have 3 things to show. We have to show that it is reflexive, symmetric, and transitive. So let's start with a reflexive proof here. So we want to show that this if and only if is satisfied if x is related to x. So if x is related to x, that must mean by our statement that 5 divides 2x plus 3x, but obviously 5 divides 5x, so we are good there. Next, we want to prove that this relation is symmetric, and we'll do that by supposing that x is related to y, and we want to show that that means that y is related to x. So if x is related to y, that means that we have that 5 divides 2x plus 3y. But now we can use the definition of 5 dividing 2x plus 3y to write that as 2x plus 3y is equal to 5 times a, and we'll let a just be some integer. So from there, we will subtract the 3y to the other side, so we will get that 2x is equal to 5a minus 3y. We can multiply both sides by 3 to get that 6x is equal to 15a minus 9y. And from here, we are going to add 4y to both sides, and we will get that 6x plus 4y is equal to 15a minus 5y. And now we can factor out things from both sides, and we will get that 2 times our 3x plus 2y is equal to 5 times 3a minus y. But we know that 5 does not divide 2, and if 5 does not divide 2, then that must mean that 5 divides 3x plus 2y. So let me go ahead and write that down. That means that 5 divides 3x plus 2y, which is what we wanted to prove to show that this is symmetric. Great. So now that we've proved reflexivity and symmetry, let's go ahead and prove transitivity. So let me go ahead and write that down for you. We are proving transitivity. And to do that, we are going to suppose that, let's say, x is related to y and y is related to z, and we want to show that this implies that x is related to z. So if x is related to y and y is related to z, then we have the following relationship. We have that 5 divides 2x plus 3y, and we also have that 5 divides 2y plus 3z. Great. And so from here, we are going to do what we did last time. We are going to break this up using the definition of divisibility. So that means we can write 2x plus 3y is equal to 5 times a, and we'll write that 2y plus 3z is equal to 5 times b, and we'll have that a and b are both integers here. Great. So from here, we want to combine these two equations, and we are going to do that in the following way. We are going to add them together. So when we add them together, we're going to get that 2x plus 5y plus 3z is equal to 5a plus 5b. And from here, we are going to subtract our y's to the other side, and we will get that 2x plus 3z is equal to, well, you can see we will be able to factor out a 5 here. We'll have 5 times a plus b minus y. And since we have 5 times something is equal to 2x plus 3z, we have shown all that we need to show that 5 divides 2x plus 3z. But if 5 divides 2x plus 3z by our definition of this relation, that means that x is related to z. Great. So we have proved that this is reflexive, symmetric, and transitive, which means this is in fact an equivalence relation. From here, we want to describe the equivalence classes, and I'm not going to get into how you could prove this, but I'll go ahead and tell you that the equivalence classes will be all integers x and y, such that x is congruent to y mod 5. If you would like to, you can prove in the comments why that is. Great, so let's go ahead and get into the next one. So for the next one, we want to give an example of a relation from the set 1, 2, 3, 4 to the set A, B, C that is not a function. So let me go ahead and get the necessary definitions that we need to satisfy in order to make this thing true. Great, so I got the following two definitions for you for this problem. So our first definition is the definition of a relation, and the second definition is the definition of a function using the definition of a relation. So let me go ahead and read those two to you now. So given sets A and B, a relation R between A and B is simply a subset of A cross B. Great. So with that in mind, our definition of a function is a relation F, which is a subset of A cross B, is a function if for all A in big A, there exists a unique little b in B such that the ordered pair A and B is in F. So in order to write a relation that is not a function, we need to write a relation that does not satisfy our for all A in A, there exists a unique B in B. So what we're going to do specifically is write a relation that violates our uniqueness. So let me go ahead and write out a simple relation that would do that. So let's consider the following relation. So consider R, which is the subset of A cross B. And those will be our given A and B up here. We'll let A be 1, 2, 3, 4, and we'll let B be A, B, and C. So R will equal the following set. We'll have 1 and A as an ordered pair, then we'll have 1 and B, and then we'll have 1 and C, and then we'll have 2 and A, 3 and C, and 4 and A. Great. So we can see that this is a subset of A cross B, as the first part of all these ordered pairs is from A and the second part is from C, but we can see we have failed our uniqueness, as for all A in A, there is not a unique B in B. Great, so let's get into the next one. So for this one, we want to consider the following function. We have big F goes from the set 0, 1 cross n to the integers, and it's defined in the following way, where f of AB is going to be equal to A minus 2AB plus B. And we want to investigate to see if f is injective or surjective or both. So let's start by checking injectivity. So reminder for injectivity, we want to check that f of AB equal to f of CD. We have that the ordered pair AB is equal to the ordered pair CD. Great, so if we have this functional relationship, we can write the following equation for these. We'll have that A minus 2AB plus B is equal to C minus 2CD plus D. Great. And so from here we can break it up into cases. So let's start with case number 1, and case number 1 will be that A is equal to 0. That's because of our definition of our function. Our A and C must come from the set 0, 1. Great, so if A is equal to 0, we can see that we can rewrite the left-hand side of our equation here to be B is equal to C minus 2CD plus D. But we can rewrite that in the following way by factoring out AC. So this will be equal to C times 1 minus 2D plus D. And from here, we want to split this up into two cases for the different values for C. So let's go ahead and first look at if C is equal to 0. Well, if C is equal to 0, then C is also equal to A. But if C is equal to 0, then we will have that B is equal to D, which is good. That's exactly what we want, that A is equal to C and B is equal to D. Next, let's look at the case where C is equal to 1. So if C is equal to 1, then we will have that 1 minus just D is equal to B. But that means that 1 is equal to B plus D, but that is impossible, as B and D cannot add up to be 1. Great. So next, let's look at case 2, which will be when A is equal to 1. So when A is equal to 1, we will have the following relationship. Well, we will have that 1 minus 2B plus B is equal to C minus 2CD plus D, but that's just 1 minus B is equal to C times 1 minus 2D plus D. And just like we did last time, we're going to play the same game where we'll check both C equal to 0 and C equal to 1. So let's first go ahead and consider when c is equal to 0. Well, if c is equal to 0, we will have that 1 minus b is equal to d, but that's the same contradiction as before, so that will not work. Our next case will be when c is equal to 1, which of course is equal to a in this case. Well, if c is equal to 1, which is equal to a, we'll have that 1 minus b is equal to 1 minus d, which of course implies that b is equal to d. Great. So that finishes this proof off, as no matter what case we are dealing with, we will have that a is equal to b and b is equal to d. Great. So I'll go ahead and write that down. We have that the ordered pair AB is equal to the ordered pair CD. So next we want to do our proof of surjectivity here. So we're going to begin by supposing that we have some integer n. And what we want to verify to prove that this is surjective is that no matter what value we choose for our n, we can map to it using our function from our codomain. Great. So let's go ahead and look first at integers that are greater than 0. So let's go ahead and note that for all n which are greater than 0, we have that f of 0 comma n will be equal to n. And that is because when we plug in 0 and n into our function, everything will cancel out except for our n, so we'll just have a plus n left in our equation there. Great. So next, let's look at the case when n is equal to 0. So let's go ahead and also note that when n is equal to 0, that f of 1 will equal n. And you're free to verify that on your own. It's simple arithmetic. And then lastly, we want to note that for all n less than 0, so when n is a negative number, that f of 1 and 1 minus n will do it. Great. So since this function is both injective and surjective, that means that this function is bijective. Great. So let's get into the next one. So for this one, we want to prove that the function, which is defined in the following way, f goes from r set minus 2 to r set minus 3, which is defined as f of x is equal to the quantity 3x plus 4 over x minus 2 cubed, and we want to show that that is bijective and find its inverse. So to start, let's start by proving that it is injective. Great. So when we're trying to prove injectivity, once again, we are going to suppose that we have f of x is equal to f of y. Well, just using the definition of our function there, that will mean that 3x plus 4 over x minus 2, and that whole thing is cubed, will be equal to 3y plus 4 over y minus 2 cubed. Great. So from here we can take the cube root of both sides, and we'll just get that 3x plus 4 over x minus 2 is equal to 3y plus 4 over y minus 2. Great. So from here we're going to clear our denominators, and that will give us the following equation. We'll have 3x plus 4, and that will be times y minus 2 is equal to x minus 2 times 3y plus 4. Great. And so from here we are going to go ahead and multiply these two things out. So when we do that, we will get the following. We will have 3xy minus 6x minus 8 is equal to 3xy minus 6y minus 8. Great. And so it's very easy to see that these minus 8s and these 3xy's will cancel out, and we'll get left with minus 6x is equal to minus 6y, which of course means that x is equal to y. Great. So that proves that this function is injective, so let's go ahead and get into the proof for surjectivity. And to do that, we are going to begin by doing some scratch work. So let's go ahead and write out that we're doing scratch work here. We want to look at f of x is equal to b, and then we want to solve for x. So f of x is equal to b will give us the equation 3x plus 4 over x minus 2, quantity cubed, is equal to b. Well, that means we can go ahead and take the cubed root, and we'll get that 3x plus 4 over x minus 2 is equal to the cubed root of b. Great. And then we can go ahead and clear our denominator there, and we will get that the cubed root of b times x minus 2 is equal to 3x plus 4. We'll go ahead and multiply that out, and that will give us that x times the cubed root of b minus 2 times the cubed root of b is equal to 3x plus 4. But we can subtract that x times the cubed root of b over to the other side, and we can subtract 4 over to the left-hand side. And we'll get 2 times the cubed root of b minus 4 is equal to x times 3 minus the cubed root of b, and then we can divide that over and we will have solved for x. So that means that x is equal to negative 2 times the cubed root of b minus 4 all over 3 minus the cubed root of b. Great. And let's go ahead and, for the sake of shorthanding our next step, let's go ahead and just call this thing a. We can note that f of a will always equal b. In this calculation we just did to find what a we can plug in for f of a is equal to b is exactly what we needed to do to find our inverse function. So we can simply write that f inverse of x is equal to negative 2 times the cubed root of x minus 4 all over 3 minus the cubed root of x. Great. So let's go ahead and get into the next one. So for this next one, we are given a function f which goes from a to b and subsets y and z of b, and we want to prove that the preimage of y union z is equal to the preimage of y union the preimage of z. So a reminder, in order to prove set equality, we must do that by the method of double inclusion. So let's start by doing the forward inclusion first. So we're going to start by supposing that we have some little a, which is in the preimage of y union b. Well, we can see that that then means that f of a is in y union b, but that means that f of a is in y, or f of a is in b by the definition of union. But we can see that that means immediately that a is in the preimage of y, or that a is in the preimage of b. But by the definition of the union, that means that a is in the preimage of y union the preimage of b. Great. So now let's do the reverse inclusion as well. So for the reverse inclusion, we are going to suppose that we have a is in the preimage of y union the preimage of b. Well, by definition of union there, that means that a is in the preimage of y, or that a is in the preimage of b. But that means that f of a is in y, or that f of a is in b. But now we can use the definition of union to say that f of a must be in y union b. But that, of course, means that a is in the preimage of y union b, which completes our proof by double inclusion. Great. So let's go ahead and get into our final problem. So for this proof, we have two if and only if statements, which means we need to prove the forward and reverse directions on both of these, which will give us a total of 4 proofs. So let me go ahead and read the statements. So we're going to suppose that f is a function from a to b, and we have x is a subset of a and y is a subset of b. So from here, I'm going to be using the terminology of image and preimage, as we have learned from lecture video 19 in this series. So we want to show that x is equal to the preimage of the image of x, if and only if f is injective, and that the image of the preimage of y is equal to y if and only if f is surjective. So let's start by proving our first statement first, and we're going to do the forward direction first. So we're going to start with the assumption that x is equal to the preimage of the image of x, and we want to get that to the point where f is proved to be injective. And then we'll do the reverse proof where we start with the assumption that f is injective and get to the point where x is equal to the preimage of the image of x. So like I said, let's begin by supposing that the preimage of the image of our big X is equal to x. And this will be for all x, which is a subset of A. And because we want to prove injectivity, we will go ahead and add on our setup for that as well. And so in addition to that, we will have A and B, which are in our domain A, such that f of A is equal to f of B. And recall from our proofs of injectivity, we want to show that that implies A is equal to B, and that will prove injectivity here. From here, we are going to define the following two subsets of A. We're going to let x sub 1 be just the singleton A, and we're going to let x sub 2 be just the singleton B. And we want to observe the following: that the image of x1 is going to be equal to the set of f acting on A, as x1 is just the singleton A. And by the same logic, the image of x2 is going to be equal to the set of f acting on b. But if you recall from our definition up here, f of a is equal to f of b, which means that f of x1 is equal to f of x2. But from our definition of the pre-image of the image of x up here, that means we can write our singleton a in the following way. We have a is equal to x1, which is equal to the pre-image of the image of x1, which from our equation above we know will be equal to the pre-image of the image of x2, which is of course equal to x2 by our assumption up here. And then that will be equal to the singleton b. But that means if we look at our extreme left-hand and right-hand sides, we have a equals b. But that's exactly what we wanted to prove that this function was injective, as we started with f of a is equal to f of b, and we ended up with a is equal to b. So now let's go ahead and do the reverse proof. And so for the reverse proof, we want to start with the assumption that f is injective and show that x is equal to the pre-image of the image of x. And since we have to show a set equality here, that means we have to do this by double inclusion. So we're going to begin by supposing f is injective. So suppose f is injective. And first we are going to show the forward inclusion. So first we're going to show that x is a subset of the pre-image of the image of x. So we're going to do that by the following. We're going to suppose that we have some element a, which is in x. So, and then we are going to consider f of a, which will be in f of x. Now we can take the pre-image of both of these, and we will get that a is in the pre-image of f of x. But that's what we wanted to show. We wanted to show that we could take an arbitrary element from x and show that it was in the pre-image of the image of x, which is what we did. Great, so that completes our forward inclusion there. So let's do the reverse inclusion. So next we will be doing that the pre-image of the image of x is a subset of x. And since we didn't use injectivity for our first inclusion, we must use injectivity for our second inclusion. So just like before, we're going to suppose that we have an arbitrary element a, which is from our pre-image of the image of x. And we want to show that that means that a is in x. And so here is where we're going to use injectivity. So that means that there exists an f of b, which is in f of x, such that we have f of b is equal to f of a. But we know since this function is injective that immediately implies that a is equal to b, but we know that b is in x, which means that we have proved that a is in x. And what did we start with? We started with an arbitrary element from the pre-image of the image of x, and we ended with a in x, so we've proved both inclusions there, and we've proved this set equality. Great, so that finishes our first proof here. So let's go ahead and get into our second proof. And for our second proof, we will begin with the forward direction as well. So we want to suppose that the image of the pre-image of y is equal to y for all y, which is a subset of b. And we want to show that this proves that the function is surjective. So we're going to take an arbitrary element of our codomain b, which we'll call little b, and we want to show that there exists an a in a such that f of little a is equal to b. That would prove surjectivity. So now we want to consider the following set. We want to consider the singleton b, which is of course a subset of b, as we have just defined little b to be in b. From our assumption, that means that the image of the pre-image of our singleton b will be, of course, equal to b. Now we're going to do a proof by contradiction to show that the inside of our image there, our pre-image of our singleton b, is non-empty, and then we can finish this proof off. So by way of contradiction, we're going to suppose that it is empty and arrive at a contradiction. So we're going to suppose that the pre-image of our singleton b here is equal to the empty set. So now we're going to break that down a little bit. That means that the image of the pre-image of our singleton b here is defined in the following way. We have f of x such that x is in the pre-image of our singleton B will be the definition of our image of that pre-image there. But now we can use our definition of this being equal to the empty set. That means that we have f of x such that x is in the empty set, because we've defined this pre-image of the singleton B to be the empty set, which is of course equal to the empty set. But that's a contradiction, as we know from our original assumption that the image of the pre-image of our singleton B must be equal to B. So we've arrived at a contradiction. So that means that our pre-image of our singleton B is non-empty. And if it's non-empty, then that means that there exists an A which is in the pre-image of our singleton B here, which is defined in the following way. We have x in A such that f of x is in our singleton B. But just breaking that down by definition, that will give us that f of A is equal to B. But since we started with an arbitrary element from our codomain and showed that we could map an element from our domain to it, we have completed our proof of surjectivity here. Great. So for our final reverse proof here, we are going to suppose that f is a function from A to B and is surjective. So let's suppose that f is surjective, and we have the following two things to satisfy. We will need to do this by double inclusion. So let's start with the forward direction first. So we'll start by supposing that we have little b, which is in the image of the pre-image of big Y. But now we can use our definition of surjectivity here. That means that b is equal to f of A for some A which is in the pre-image of Y. But A being in the pre-image of Y directly implies that f of A is in Y. But because we know that f of A is equal to B, that means that B is also in Y. So we took an arbitrary element from the image of the pre-image of Y, and we showed that it is in Y. Great. So now let's do the reverse inclusion. So for the reverse inclusion, we are going to do the reverse. We're going to start by supposing that B, an arbitrary element, is in Y, and we want to show that that means it is in the image of the pre-image of Y. So from here, we're going to take a little a, which is in our big A, such that f of A is equal to little b, again by surjectivity. And since we know that f of A, which is equal to b, is in big Y, we know that A must be in the pre-image of Y. But if A is in the pre-image of Y, that means that f of A is in the image of the pre-image of Y, but we know that f of A is equal to b. So let me go ahead and write that out. We have b is equal to f of A, which is in the image of the pre-image of Y. Great. So that finishes this last proof off, and that's a good place to stop.